Welcome to A-Star Science, part of our Chemistry A-Level series. Today we're going to be talking about Kc and equilibrium. Kc is an important topic. It serves as an introduction into these equilibrium constants. So K basically just stands for a constant, some constant, and you're going to see K used a lot in A-Level chemistry. In this case, the C stands for concentration. So when you're talking about Kc, you're generally talking about aqueous solutions. You also see that constant K used later on. You'll see it for Kp, which is for pressure. You'll see it for Ka, which is an acid-base equilibrium constant. And you can see it for Kw, which is similar to Ka, but in this case, it involves water. So doing Kc and equilibrium is really important because it serves as an introduction on how to use the Kc concept and the constant concept for many other parts of the A-level syllabus. So when we're talking about Kc, you're talking about the concentration of products over reactants. And of course, we use the square brackets to indicate concentration. So Kc is just a ratio of products over reactants. Now, in the exam, you'll see, for example, in this question, that at the bottom they say, give an expression for the equilibrium constant, Kc. So when you write the expression, you're going to write the products over the reactants as the chemical symbols. So in this case, for this equation, which I've circled here in red, the Kc is going to be the products, which is C, over the reactants. The Kc expression will be the products over the reaction. Now notice there's a 2 here, 2 moles of B. So we put that as a superscript, as an indices for the particular reactant or product that it is aligned to. And that's how you would do the Kc expression. Products of a reactant, and you indicate the number of moles by an indice based on what the number of moles is in the reaction. Okay, so let's look at another part of doing Kc. And if we look at the question itself, again, here, question A, it says a solution containing 0.6 moles of A is added to a solution containing 0.6 moles of B. The amount of C formed at equilibrium is 0.28. So this is an important time to bring up the fact that Kc is used only in reactions that are at dynamic equilibrium, which we can tell when it has this sign, the reversible reaction sign. So it's saying that at equilibrium, it's given us some amounts. And we're going to use a specific technique called the ICE method. ICE, the I in ICE stands for initial moles. The C stands for change of moles. And the E stands for moles at equilibrium, or equilibrium moles. So the way you use the ICE method is, you're going to write out the equation again above the ICE table. And then we're going to indicate the information that's given to us in the question. In this case, it says the solution contains 0.6 moles of A and 0.6 moles of B. And at equilibrium, which we can draw a line underneath here, at equilibrium, C formed 0.28 moles. And they want us to find out what A is at equilibrium and what B is at equilibrium. Well, for an equilibrium reaction, when one thing goes down or up, let's say this one goes up, then the other side must go down. So here we can see that C, initially when the reaction started, there was 0. There was no C because the reaction just started. But at equilibrium, it was 0.28. That means that the change of moles was plus 0.28. So if this went up, the other side must go down. Well, A must have went down by 0.28, and B, which is 2-to-1 ratio, must have went down by twice that amount. So let's just use our calculator really quickly. 0.28 times 2 is 0.56. So B would have went down by 0.56. So now we can determine the amounts at equilibrium. 0.6 minus 0.28 is 0.32, and 0.6 minus 0.56 is 0.04. So this is a nice way of working out equilibrium reactions and the changes of moles by using what we call an ICE table. And in fact, I use this method for Kp, I use it for Ka, for some of the more complex equations in Ka, like buffer equations, as well as for Kw. This ICE table idea is going to be very important. So let's look at a more difficult question going forward. So let's look at a more difficult question here. We can see that they're asking us to calculate the amount of moles of oxygen at equilibrium. This question is more difficult than the first one because it does not give us the equilibrium mixtures at the start. It only gives us the amount of moles, at equilibrium, not the initial moles present. So we can't use the ICE table method in this case. But what it does give us is Kc. So we can basically use the Kc expression and work backwards. So first, let's answer the first part of the question, which is to give the expression. Kc is products. This is the product, SO3. And it's 2 moles of that over the reactants, which is SO2. 2 moles of that, all times oxygen, 1 mole of that. So we would have got the first part of the question correct. Now, how can we find the moles of oxygen present? Well, we can use the information that they've given us because we know that Kc equals 15 mole minus 1 dm cubed. So here on this side, I can write that this whole thing will equal 15 mole minus 1 dm cubed. So now if I substitute in the information, because this represents equilibrium, this Kc represents the constant at equilibrium, which they've given us here. So we can substitute the information in. So at equilibrium, it tells us that there was 0.461 moles of sulfur trioxide. Remember though that the square brackets indicates concentration. So we need to turn that into concentration. Concentration is moles per volume. They give us the volume here, which is 1800 in cm cubed. We know that we want the volume in dm cubed. So that converts to 1.800 dm cubed. All of that is, remember, this is squared. And then we can do the SO2. Which is 0.176 divided by 1.8 dm cubed. That's squared as well. Divided by O2, which we don't know. So we're just going to leave that as X or O2 or question mark. So now let's do some calculations, which I'll do. I'll pause the video and then I'll get back and show you how we can just solve for X. So I've done some of the initial calculations and now we're going to continue the calculations. So if we keep going, from the calculations we had 0.256 squared. So if I do that on my calculator, I'm going to get 0.0656 all over 0.0978 squared. Remember, we're squaring because of the coefficients, and that is going to be 9.565 times 10 to the minus 3, all multiplied by X. So now all we need to do is solve for X. So if you solve for X, the final answer will be 0.457. 0.4, just read the calculator, 0.457. And you also, we're not going to do it in this video, but you also would have to do the same process for the units as well. 3 mole to the minus 3. Okay, so you'd have to do the same process for the units as well. Now that gives us the concentration of the oxygen. Remember, this is the oxygen which we made X. But we're trying to find in the original question the amount of moles of oxygen. Okay, so as we know, that little formula, that concentration is moles over volume, and we want the moles, so we need to multiply this by the volume, which was 1.8 dm cubed, and that will give us a final answer of 0.823 moles. So that is a more complicated type style question, one where they gave us the Kc here, and they gave us 2 of the equilibrium moles, and then 1 unknown. And we were able to work backwards and find out the unknown by using the Kc expression. So whether you have to do an ice table to find out the amount of moles at equilibrium, or you have to work backwards from a Kc. Remember, you can find Kc by just doing products over reactants and making sure that you use the moles, number of moles, as subscripts, and it will be quite easy. Please make sure you like and subscribe to this video, to this channel, and let me know if there's any videos you'd like me to do, any topics you'd like me to do, so you can pass your A-level chemistry.